So let me talk about subatomic particles a little bit. So there's three main subatomic particles, aka a particle that's smaller than an atom, or that atoms are comprised of. There's protons, there's neutrons, and there's electrons. So protons and electrons are paired, kind of in the sense that they kind of need each other to exist. A proton has a positive charge, and an electron has a negative charge. Usually, -1, and then a proton has a +1 charge. A neutron is named that because it is neutral, hence neutron. A proton is kind of heavy, an electron has almost no mass. A neutron has a ton of mass. So uranium in a core or in a reactor like this, there's a couple different types actually. So an element, or your atomic number or something like that, is the number of proton-electron pairs. So hydrogen, for example, is the first in the periodic table. It's got the name of atomic number 1 because it has 1 proton and 1 electron. Oxygen, for example. Oxygen, I'm pretty sure, has 8 protons, 8 electrons. The neutrons are usually the atomic number plus a little bit. It's a little different for neutrons, though, because it's something called an isotope. So an isotope is the same element, but it has a different number of neutrons. So there's 2 types of uranium mainly in our core right now. Uranium-238 and uranium-235. The difference between those two is 4, or 238 minus 235, 4. It's 4 neutrons of difference. So in our core, uranium-238 is not fissionable. It is fissionable. All atoms are fissionable, but it doesn't like to fission. It takes a lot of energy to do that. Uranium-235, on the other hand, likes to fission really quickly. It likes to break apart on its own. And doing so, in that process of splitting, it releases energy. It releases 2 split, parts of the whole. And then it releases between 2 or 3 neutrons. And neutrons are what causes fission. Think of them like bullets almost. Bullets whizzing around in a core, and they whiz around and they hit these uranium atoms, and they split, and they create more bullets, which whiz around and they break even more off. And it's a chain reaction. You've probably heard that term before. So the thing is, let me think for a second. How do I explain this? We want to control that. If you don't control your chain reaction, what do you get? You get a bomb. You get an atomic bomb, a nuclear bomb. And the way that we can control our chain reaction is through something called a control rod. This is very particular to this kind of reactor. It's made of a neutron-absorbing material like boron, or hafnium, or some other material. And that boron essentially will eat the neutron, or it will eat those bullets before it has a chance to go around and hit another uranium to cause a fission. So our core right now, do you see all those green indicators? They all say full in. That means all the control rods are fully inserted, which means they kind of, like this diagram right here, this is a cross section. So it looks like a cylinder. The core looks like a cylinder. And the control rods kind of go inside the cross section from the bottom. It goes through the cylinder from the bottom, and it kind of cuts off any reactions that could happen from one side to the other side of the core. If we withdraw the control rods, the reactor heats up. It heats up because the control rods are no longer there to remove neutrons that could possibly cause a fission. Okay, so now I guess we can say if we removed all the control rods, we have all of this heat. All this heat is in the uranium, but the question is, how do we remove that heat? In this reactor type, it is a boiling water reactor, but boiling water reactors are a subset or a category of a light water reactor. So there's two types of water, kind of you want to consider is heavy water and light water. Light water is just normal water. It's water you would drink. We don't need to worry about heavy water too much because not in this game. Water is passed through the uranium fuel rods, which are in this cylinder. They come from the bottom, they flow up to the top, and as they flow through, they kind of exchange and they take heat away from the uranium fuel rods. In that process, they're allowed to boil. The water is allowed to boil into steam. That steam travels through pipes. Those pipes come to the turbine, just like in a coal power plant. And what we do is we bring this up to speed, we synchronize it to the grid. It's a little bit more complicated, but I'll teach you more about that later. Underneath the turbine, after the kinetic and thermal energy has been extracted, that's what a turbine is for. A turbine converts kinetic energy and thermal energy into rotational energy on the shaft. And the shaft turns a generator, and the generator pushes electrons around, which creates power. It's change, it's movement of electrons. So underneath the turbine, or at the end of the chain, I guess you could call it, after all of the energy has been extracted from the steam, it needs to be condensed back down into water before it gets put back in the reactor to boil again. The way we do that is with the condenser. You see that diagram up there? So steam kind of flows down from the top. It goes through, it's just another heat exchanger. And it goes through a bunch of coils. There's like thousands and thousands of coils inside of a condenser. And these coils contain really, really cold water that's usually pumped from a lake or a pond, or in our case, a cooling tower. A cooling tower is yet another heat exchanger. It exchanges heat with the surrounding air. So then, after all of the steam has been condensed back down into water, it is pumped out into there's a couple stages. I'm trying to figure out how complicated I want to make this. How complicated do you want it to be?
Zam, I mean anything you feel fine for me. This is like a class lol.
I guess. I'm trying to figure out how to start with the basics first before we move on. I guess I'll tell you about it. So in our system, the water that the steam that gets condensed into water, it's called condensate, because it's condensed water, condensate. The condensate is pumped into something called the deaerator or the deaerator, however you say it, deaerator. The deaerator kind of de-airs the condensate. The condenser is a really big object, and it has leakage, and you don't want to be putting in air, like aka nitrogen, oxygen, different things in the atmosphere. You don't want to put that into your reactor core because that will cause damage over time. So you want to remove those, what they're called non-condensable gases, from your condensate, and it's used with a deaerator. This is the deaerator panel. It's just it's similar to a boiler. It kind of like moves the condensate around using heat and stuff. and then all those gases will kind of be desaturated out of the water and be able to be vented out of the system. So then, at the bottom of the deaerator, it gets drained and it goes into your feed water pumps. They're called feed water because they feed water into your reactor. And these pump the kind of cleaned up water that comes out of the deaerator into your pressure vessel where your core is held. And then it gets heated up again and it turns back into steam. All right, I think that's pretty basic. I'll look around for some pictures in a second, but do you have any questions?
All good, sir.
Okay. All right, 1 second. Let me see if I can find some references for you. Most of them are a little... Oh, wait. I have one. I made one a while ago. I remember now. Did I lose it? I'm gonna lock it. Yes. 1 second, bro. My bad. Alright, I found it. I'll send it to you. Alright, do you see that image?
Yes, sir.
Okay, so you can see on the left the pressure vessel, and you can see the core, and you see the water and the steam coming out. It goes through those steam lines, and it goes to the right and up to the turbine. The turbine then extracts energy from it, and it goes into the condenser, which is right below it, which will then pump it through back out through the deaerator, which I did not illustrate very well, goes back into the reactor core. Your emergency systems in this diagram are in red. The circulating water is green, stuff like that. It's really basic. Here, follow me. There is one in this facility. There used to be one just on this wall over here. I forgot. Are you coming? Hello? All right, there you are. There used to be a map or a diagram in this room, but they got rid of it for some reason. So I'm gonna show you where one is. We'll kind of talk about it a little bit. I don't know why they removed all the diagrams. There's only one left. It's right here. So you can kind of see the similarities, right? So there's your reactor pressure vessel, there's your core. The water around it gets boiled into steam. I wish I had a laser. It travels to the turbine where it goes through, turns into condensate, gets cleaned up, and gets put back in the pressure vessel. Okay, let's go. Do some practice, I guess. So I'm going to go through, I'm going to explain each one of the systems here. So here's your emergency panel. This includes two things mainly. First of all, the RCIC turbine, or reactor core isolation cooling. I forgot exactly. But basically, this is a zero power method of cooling the core. It only uses excess steam. So steam that gets diverted from the turbine or bypassed gets pushed through this turbine, and this turbine is attached to a pump. And this pump pulls water from a storage tank into the core. And it's just a method of cooling the core when you have no power during an event like a loss of offsite power. Next to it is the Lipsy valve, which is known as the low pressure coolant injection. So a phenomenon that you should remember for all liquids and gases and pretty much everything is that so liquid or water in this example, its boiling point changes with pressure. So if you have a higher pressure, it means the boiling point, aka the point where it goes from liquid into a gas, aka steam, it goes up. So if you have more pressure in your pressure vessel, more steam, it means your temperature will go up as well, which means it's more efficient. Efficiency of a thermodynamic cycle is directly derived from the hottest temperature in your system and the lowest temperature in the system. So the greater difference you can make that, the more efficient your cycle is. Okay, so basically, I'll give you the rundown of it. If you lose power, turn this on and turn this valve. That will open up the steam valve fully and it'll start injecting a ton of water into the core, hopefully cool it down. It's only really useful when you have a ton of pressure in the core because it needs steam to operate. If there's no steam to operate it, then it can't run the turbine, it can't move the pump. If there is no pressure, that's what you use the low pressure injection pump for, the Lipsy valve. This takes water from the same place and it pumps it into the core if the pressure is low. All right, moving on. So next panel. These are the shutdown cooling pumps. They're basically just other heat exchangers. They take water that goes through the core with pipes and they exchange the heat with the surrounding environment like a service water system. And it kind of rejects heat so that the water can't boil. It keeps the reactor at a cold enough temperature to stay stable or stay fat. Up here you can kind of see a diagram for it. It's not the greatest. Let me send you a better one because I have made some better ones before. Okay, don't send this one to anybody. This is a kind of confidential one I'm working on right now. Do you see it?
Yes, I
Do you
see
see the
it.
image? Okay, cool. You can kind of see the core in the center. The water is on the sides. It travels down to the bottom where it goes up through the core, turns into steam. You can kind of see those pipes leading up, and it goes in the top section, or the head turns into it goes into the main steam line and exits. The upside down light bulb shape on the outside is known as the containment structure or the dry well. You can also see the light bulb shape right here on this diagram on this panel. I don't know why I told you that. That's kind of useless to tell you. Anyways, let's move on. So we're going to skip this rod panel for now. Over here are the recirculation pumps. What these do is they push water through the core so that it flushes out something called a steam void. So as water boils in the core, it creates a little pocket or a little bubble of steam. And that little bubble of steam is bad at neutron moderation. It doesn't moderate your neutrons. So that's another thing I forgot to mention. Uranium atoms, they don't split using just any old neutrons. They use, or in this core at least, they use something called a thermal neutron, aka just a slow neutron. When neutrons are born from fission, they're fast. So they have to be slowed down so that they have a greater chance of hitting a uranium atom and causing a fission. In other words, these create more power. So recirculation pumps increase your power in your reactor. All right, next is the turbine panel. On the left over here is their main valve. That is kind of like a really big valve, and it allows you to admit steam into the turbine. Next to it is the generator breaker switch. That is what enables you to sync to the grid and start pushing power to the grid. Above it all these buttons and stuff, those are set points for automatic runoff. Below them, these valves down here, these are bypass and steam valves. For startup, before you start up the turbine, you're going to want your bypass to be at some number. Some people use 30, some people use 50. Basically, it just reroutes steam around your turbine so that it doesn't start turning it when you're not ready. And it also relieves pressure in your system. So we're gonna open this up all the way right now. You can kind of see that's what I'm doing. 90%, 92, 95, or 100% bypass. Okay, over here, this is the main cooling circuit panel. You can kind of read the labels up on the upper left here for every panel. This is probably the most complicated part of the entire system, and honestly, I don't expect you to master it until you've put in another probably 5 or 10 hours. It's not terribly hard though, so I'll do my best to teach you it. What it is just you're balancing the flow of water, because the entire system, the entire power plant is just one big loop. Water goes into the core, gets heated up, comes to the turbine, goes to the condenser, goes to the pump, goes to the core, goes to the turbine, goes to the condenser, goes to the pump, goes to the core. It's just a loop. You know, it goes around and around and around and around. So this panel right here manages the flow through the loop. I guess that's all you really need to know. Over here, auxiliary panel. It contains the condensate storage tanks, the pumps for them. That's like excess water, because you're going to have leakage at some point, whether it be like a malfunction or, you know, you just wasted steam for some reason by using like a relief valve. You would use the makeup pump or the drain pump or whatever. Whoops. You would do that in order to kind of make up water in your circuit or your loop. All right, over here is the condenser. We already talked about this a little bit, but it just rejects steam from the turbine, turns it into condensate, and gets pumped out. The deaerator, I told you it removes non-condensable gases, it cleans up your condensate. And then over here is the electric panel. I love these things. Okay, so I wonder how we're going to explain this one. So think of, in an electric diagram, water usually flows above to down, like from top to bottom. And think about it like water. Think of power like water in this case. Water comes, so if you look at the top, you can see line B. It comes down from that black line, goes through that startup transformer and that breaker 52 BA2. You don't need to remember these names. It's just the startup breaker, startup transformer, and it powers bus A. A bus is just like a joining or like a group of items or systems. Anyway, all of those pumps that you can see, all those red lights on, are all on that bus. Down here is the safety stuff, or the safety circuit. On your left over here, you got your diesel generator. I'll click it for you. Well, I can't yet. There's the startup spark, so that brings power to the EDG bay so they can be started. And this right here is your diesel generator switch. That turns it on in case you have a loss of off-site power, so you can power your safety systems during like a shutdown or something. And then this one right here, don't worry about that. This one right here is what powers the safety bus or the safety circuit from the diesel generator. Okay, the white, you see the white lines at the bottom, that's your battery bus, that's your DC bus. It'll pretty much always be active unless your battery is completely drained, which it probably won't ever, because it's kind of hard to get to that point. The lights are down there at the bottom. stuff like that. Basically, you want to keep this green line always powered. And you do that by following the flow of water. So you flow, in this case, our power is flowing from the black line at the top. It goes through that breaker to the orange line. Then it goes down to the green line, goes through that breaker, and it powers our green line bus. A little confusing right now, isn't it? Okay, we gotta get a drink. Okay, so just remember, if at any point you have questions, just ask me. It is going to be a bit much until you start learning it. Okay. I think we should probably do a startup now. What do you think?
Sure.
Okay. So first thing we're going to do, we're going to do a walk around. We're going to look and make sure nothing is, in an emergency state. I would call an emergency state where your reactor level is low. Right now it's kind of low. You can I wish I had a light, but you can see these little red bar graphs right here. They're kind of your range to give you context of like how close it is. If your reactor level goes too low, the core will start melting and you'll hear alarms and stuff. By that point, most automatic systems will flip on and it will try to save itself. But if you've put it in bad circumstances, then it will probably die. It'll probably crash the server. Okay, so that's not bad. It's okay. The reactor level, -2 meters, is decent. It's not what I would want, but it's okay. And then the second thing I would call an emergency is if you have no offsite power. Right now, we have offsite power. Line B is powered. You can see the green light at the top on the black. And then bus A is also powered. You can see that green light too. So now, time to work on our plant systems. First thing I usually do is turn on pumps. So first you open the inlets, so feed water pump inlets and outlets, and then the starter. You can also do it in any order you want. It doesn't really matter, but professionally, if you want to do it professionally, you always open the inlet, then the outlet, and then you start the pump. Okay, that will enable the feed water pump. This, will let us put more water back there. So we're going to do that now, just as a little exercise. Do you see the pump 1 speed setting? It's a little dial. Do you see it? Right? Yeah, I think you're looking at it. I just want you to turn it on a little. Okay, yeah. Turn it on a little bit and bring the reactor level to 0 meters. Essentially, right now we're taking water from the deaerator. Actually, the deaerator is dropping pretty quickly. We might want to, don't let the deaerator get too low. So go ahead and stop it. Well, you have to go negative to go down in speed. You can do speed 2, by the way. So you can go negative, like negative like this. See? There you go. All right, we put a little bit of water in the core. You see that? We went from -1.9 to -1.6. It's a little bit better. Okay, now we do, there's a bunch of things we can do. So condensate pumps, do you see them? Condensate pump 1 and pump 2 right here. It says cond pump. That's 2.
Yeah, I see it.
Okay, yeah, turn this on. Yep, And then up at the top, turn on all of the polishers and then the preheaters. So the preheaters just take excess steam, not excess, it's kind of just like vented off of the main steam line, and it's used to preheat the water going into the reactor vessel so that the reactor doesn't have to do so much work to heat up our water. It kind of, it's more efficient to do this. All right, second thing I would do, I would always make sure you have at least 5 or 6 meters of water in your CST tank. Right now we're at 4.7, so you're going to want to use the makeup pump over here, CST makeup pump, and bring us above 6 meters of water. There you go. Now, you have to be careful about this kind of area right here. The condensate makeup, drain, and then the hot well makeup and the hot well drain pumps have a very large power draw. And if too many of them are on at the same time, you could crash your grid. So let me kind of show you what happens if you do that. Oh, I don't know why it's not working. Whatever. Anyways, it'll kind of break your situation. Yeah, you'll see it later. All right, now turn on the automatic control and the auto hot well level control. Up at the top up there. Yep. All right, now the main cooling circuit is managed by the automatic control, and now we can move on. So now is condenser. We want our condenser to be able to vacuum because then it better effectively condenses steam. Unfortunately, it won't get there until it has steam. It's a very peculiar circumstance because of these guys right here. These are called SJs, otherwise known as steam jet air ejectors. They work off of something I think called the Bernoulli's principle, forgot exactly. But basically, as a gas moves really fast or a liquid, as it moves quickly, it creates negative pressure or like a lower pressure region. That's how wings work. That's how lift works. As air goes really fast across an airplane wing and across an airplane's wing, it creates a negative pressure on top of the wing, thus dragging the airplane upwards. This is a similar principle where the steam is admitted through the SJ nozzle, and it kind of creates a negative pressure which drags air out of the condenser, thus creating a vacuum. So we can turn these on now, and I would put them to 100% because you don't really need to do much fiddling with them in Unit 1. So if you're going negative right now, you're going to want to go positive for both of them. And turn on the pumps. Or sorry, the nozzles, yeah. Yep, go positive for both of them. There you go. And just let it go up to 100. Nothing's really going to happen right now because we don't have steam in our system, so the SJs can't function. If you want to, though, we can do it early. The second thing here, you have the cars. The cars are the condenser air removals. They're just normal pumps. They just pull pressure out. So do you see the condenser pressure gauge? It says 1013 millibar right now, or 1.01 bar. Do you see it? It's right here.
Yes, I see.
Okay, so go ahead and turn on both cars, and then you should see the pressure go down. There you go, see that? The pumps, the car pumps are taking air out of the condenser. They're pretty slow because they're small pumps. Yeah. All right, next is the condenser rec pump. I don't know what that's supposed to be. It circulates water through the core. It's that green line on the diagram up there. It circulates, sorry, not the core. It circulates cold water from the cooling tower or the lake through the condenser so that it can cool down steam. So turn on both of those and then turn on the automatic control. Yep. Okay, now deaerator, you don't need to worry about it too much. Just turn on the auto. Turn on the auto. Yep, boom. Okay. If you're unsure about yourself, I would always turn on the diesel generators. And if you don't want the lights to go out, which I did, let me show you. So you would turn on this bottom breaker 52 DC1, this one right here on the bottom that leads to the blue, leads from the white line to the blue line. That essentially guarantees you'll always have lights in your facility. Then turn on the startup spark, the spark thing, and then the diesel generator. And this will run up your diesel generator. You can see the gauge right here, the RPM. It will run it up, and it will always stay active because Unit 1 is simple, and they don't care about fuel levels or diesel fuel. So this essentially will make sure that your circuit will pretty much always be safe as long as this one up here is activated, which our diesel generator isn't active, so we can't turn it on yet. Okay, over here, turbine bypass is on 100%, so we're good there. Now is the recirculation pumps. So go through the order I told you. So inlet, then the outlet, then the pump. Yep, for both of them. These things are twins. You always want them to be identical in both flow and power and everything like that. So turn on pump 2 as well. The inlet, outlet, stuff like that. There you go. Okay. Over here, this is kind of, if you think about it, it's our point of no return. If you turn off this shutdown pump right here, our reactor will start to heat up. It'll be really, really slow because we haven't pulled any control rods yet, but it will heat up. So if you turn this off, just be cautious because we will now be starting the reactor. So, you ready?
Yes, sir.
All right. Go ahead and turn it off. All right. It's not immediate, as I told you. It's going to be slow, but just be, see, it already went up. Look at that. 31 degrees already. See? 31 Celsius, 32 Celsius. It's already warming up, and we haven't even moved any control rods out. Anyway, so now we do control rods. So do you want to do it manually? Because we don't need to. We can just do automatic. I just think rods are fun. That's
Sure, let's do manually.
Okay, so first, so turn your rod control speed to fast, or F. There you go. And now withdraw rods. So click the rod control to withdraw. The little lever. There you go. All right, now we're pulling. So let me tell you about that little number on the left, reactor period. Reactor period is a kind of rate of change measurement. What it measures is how long in seconds it takes until the reactor power increases by a factor of E. E is a mathematical logarithmic constant. It's approximately equal to 2.71-ish. So right now, in about 570, 50, 60 seconds from now, reactor power will be 2.7 times what it is. Right now we're at 0% power. I mean, you can see the big zeros everywhere, but we'll get there. So we'll be 2.71 times 0. We'll be slightly more than that because we are at a slight power level. Anyway, what reactor period kind of means is that if it gets really low, it means your reactor power is increasing really, really fast. So the reactor will trip. It will scram itself if it goes below 20 seconds. What that means is 20 seconds from now, your reactor power will basically be doubled. And that could be really, really bad if you're operating at something like 80% power. So imagine going from 80% power to like 160% power in like 20 seconds. That's a big jump. So it'll scram itself. In our case, we only need to worry about it just a little bit during startup, because as we pull more rods out, our core kind of gets more sensitive to change as it creates more neutrons and more fission. So it will go down and down and down. And once it starts to get around 30 seconds, I'm going to want you to either change the control speed to a slower setting, like medium or slow, or if you feel cautious, just stop withdrawing completely. Just put the lever at neutral. Does that make sense? Yep. Okay. It is a little much right now, isn't it? We'll get there. So we're under 100 seconds now. In real life, they would never let it get this low. This is like egregiously low in real life. But this is RBWR, it's a game. We can handle really low periods and we'll be fine. So once it starts getting around 40 seconds, just be cautious. And if it hits 30, you'll hear a low period alarm go off. It's okay, as long as you don't let it go below 20. So right around, I'd say 35, either change your speed or just stop withdrawing. That's good. You're doing good. Don't worry. But you can kind of see how that worked. Like as you slowed down the withdrawal of control rods, it got more stable, of course, because you weren't changing power. And as you get more stable, the period should go up. So you'll hear an alarm in a second. Oh, I guess not. Yep. All right, give it a second. There it is. It's okay. All right, go ahead and slow down so you don't scram. All right, perfect. Now, just wait it out. Or if you feel risky, put it on slow and keep pushing. The closer you get the reactor period to 0, the faster your reactor will start up. So that's why some people go for like 21 seconds. Like they feel really risky. They like to push it. So another thing I gotta tell you about, water. Do you remember what temperature water boils at? If you ever learned it in school or whatnot?
"100, right?"
Nope. Yeah, 100 Celsius. So right around 100 or 110, because, this is a simulation. They didn't do it that well. I don't know what that alarm's for. Oh, high IPR. Oh, you already understand that. Okay, cool. Yeah, right around 100, we should start seeing steam pressure come in. Okay. Well, that's cool. You understand what IPR is. IPR, I'll explain it anyway, I guess. Intermediate power range, or in this case, power range monitor. It's just like a mediary startup monitor. It tells you what the power level is when you're at very low powers. It's essentially just a really sensitive stick that they put in the core. Yep. All right, keep increasing. Well, IPR I meant. There you go. You usually want to shift up in IPR right around 70 or 75% IPRM. So just give it a second. And your period is decently high now, so you can keep cranking the rods out. There you go. Good work. And as you increase power, it will get more sensitive. So like, remember when you could do it on fast speed and it would barely change the period? But now you're on slow speed and it's changing quite a bunch because it gets more sensitive. Yep, but yeah, anyways, just don't let it go below 20. Most people don't let it go below 30. So you may have people argue with you on that fact in public servers. It's okay though, because it won't scram until 20. And there we are. We are above 100 degrees and we have some steam pressure. We're at about 25 kilopascals right now. Atmospheric pressure is at about 10. Pretty sure. No, it's at 100. So we're kind of at a vacuum. And right about 100, it should be like atmospheric. We want to bring that number to about 7 MPa. Or 7,000 kilopascals. We're at 90 kilopascals right now, so we got quite a while to go. And look at that. We are at 1.3% APRM, aka reactor power. And at this point, your IPRM is going to be kind of useless because it goes out of range. So now it's time to keep increasing the APRM now. For startups, you can run up your turbine and your whole reactor anywhere between 10 and 35% APRM. So we're at 2% right now. Let's aim for right in the middle. I want you to bring reactor power to 20%. Think you can do that? Let's go. So go ahead and keep withdrawing rods. You can probably do fast mode now. The reactor should be stable enough to not have a low period problem. Hopefully. I mean, I might be wrong. As it gets higher and higher in power, it should become more stable. Yeah, it's getting there. Yeah, see, it slows down and it's going back up. See, I told you. As it gets more powerful, the neutrons flow around and becomes harder and harder to make a really big change in power all at once. So period, of course, will go back up. So you're at 5% APRM. You see that, right? Right in the middle. Yeah, the reactor can go all the way to, pretty sure 128 or 126% APRM. Yeah, usually the turbine will have issues before that point. All right, 10% power. And just bring it to 20. By this point, you should be boiling quite a bunch of water. So you're going to want to look around the rest of the room and make sure things aren't broken or having issues or anything like that. So looks like everything is doing okay. Like our reactor level is positive, so that's good. Condenser pressure, it is right in the middle of the line, or it's about 15 millibar. That's perfect. We want it to be at that point. What's that alarm? Oh, no recirculation flow. That's okay. The tutorial will have you put recirculation pumps at 28%. Or watch your power, bro. You might want to go negative, honestly. You might want to insert some rods. You're at 30% power right now. You might want to decrease power. There you go. You can do a sync on 30%. Like, it's okay. It's just the bypass starts having a lot of trouble. Like, it can't deal with that much pressure once you go above about 35% power. All right, I'm gonna leave you to it. Just take it to 20%.
What does auto balancer do?
So auto balancer changes kind of, oh, your power is dropping pretty quick. Yeah, there you go, just compensate for it. There you go. Okay. Auto balancer kind of balances the temperature of the rods, and you can see the temperature of the rods right up here. You see the Pepsi looking logo over the top. What is that alarm? Oh, nervy circulation plug in. Okay, you see the Pepsi looking logo up here? See that, the red and blue? Red, white, and blue? Yeah, that thing. That is kind of your temperature graph. Or, well, in our case, it's not really temperature. It's the balancer is known as the rod worth minimizer. What it does is it kind of like balances the axial, or so the radial, like, power distribution. Because if you think about it, it's like this kind of looks like a sphere right now. The core kind of looks like a sphere. So in the center, there's going to be more reaction because it's surrounded by more material, more uranium. So it's going to be hotter in the center. Whereas on the sides, it's surrounded by more water, more coolant, more steel, or neutron absorbers, stuff like that. So it's going to be colder on the outside. So what the balancer does is it kind of balances out so that each rod is equivalently the same power level. It's a little confusing. Anyway, you can just leave it on fast. Yeah. Yeah, you can go ahead and turn it on. There you go. And it'll push some rods in, it'll pull some rods out. It'll take that red and blue shape and it'll make it more balanced and white. All right, you've done pretty good on the power level. So now we can probably move to turbine. So right now, our steam pressure is 5.7 MPa, or 5,700 kilopascals, with our pressure rate being right about 1. That means it's not really changing. So if you decrease the bypass like this, our pressure should go up because we're letting less steam be bypassed from the system. See? And we want it to be above 6 MPa for turbine start. Ideally, you want it to be about 7. So decrease the bypass until the steam pressure is at about 7 MPa, and then open it back up again to balance it and get the pressure rate to be right about 1 once you get to 7 MPa. You want it to be stable at 7. Yep, there you go. Good work. That's perfect, bro. All right, awesome work. Okay. Yeah, you don't gotta fiddle with it too much. Yeah, you got within the range. That's good enough. All right, so now we can open the turbine main valve and we can start running up the turbine. There you go. And we're gonna use the auto run up because it's a little hard to do it manually. So put it on fast. I already clicked 3,600 RPM. So just put it on fast speed and then do the auto accel. There you go. And then fast, or sorry, turn on the auto RPM. There you go. And there it is. RPM is going up. And it should auto balance the inlet and the bypass right at about 7.1 MPa. So you can see he's pushing it He's working on it. Just let him have it. Turbine sync. It's essentially where we match the phase of the generator with the phase of the grid. And the way we do that, we have to match frequency at the same time. If your generator is behind in phase or too forward in phase, it could kind of yank it. It's happened before. It causes a lot of damage, and you don't want that. I mean, it doesn't happen in game, it just doesn't let you sync. But in real life, it does cause damage. So the little synchronous right there with the little dot spinning around, that measures your kind of like difference in phase. You want it to be where the dot is directly at the top, where it says sync, and it'll turn green. You'll see it later. And then you also want your RPM to be 3,600 or 3,600 RPM. That's frequency. Vibration happens. I think there's 2 peaks where vibration happens, so like 1, 1 and 2, 3. Anyway, we're getting there. Alright, it's getting there. So now you're good. Essentially press the generator breaker switch when it's ready to synchronize. So we are within range for RPM, but we're not within range for phase right now. Do you see the synchronous? The little red dot. Once it gets to the top, you're going to want to click the breaker. And now. There you go, perfect. Okay, now we're going to want to inlet a little bit of steam. So, inlet some steam. Use the inlet, the main valve, and let some steam in. There you go. Okay, see, now we're making power. And you're going to want to fully close the bypass. So close the bypass because it's just wasting steam that could otherwise be used for power. All right, and essentially once that's closed, the auto control can take over. So put both of the valves at neutral. Put them at neutral. Oh, okay, well, might have issues here. And then click the auto, perfect. All right, that was a little close. We don't want to let the pressure go too low, otherwise it will just trip the turbine. What's that about? Deaerator is having trouble. I hate the deaerator. Everybody hates the deaerator. It's always complaining. It just complains about the slightest difference in anything. Okay. So we are currently making 50 megawatts. You can see it on this green thing up there. Well, 40 now, 30 now. We don't have a lot of steam. So how do you think we make more steam? How do we make more steam for the turbine? What's the big heat source? What's the big boiler in this nuclear power plant?
Increase heat.
Yeah, increase heat, but how do we do that? What did we originally do to start boiling water? The rods, yeah, there you go. Now, we did drop in power quite a lot, probably because our pressure is dropping, so yeah, keep pulling rods. Now is the time that using recircs would be okay. They're a very quick way to increase power because they flush out the steam voids, but they do draw a lot of power. So you only really want to use a lot of recirc when you have your grid switched over to using your turbine. We have not done that yet because we are not producing a lot of power. Once we start making enough, like right around 100 megawatts, we can switch over. Yeah, we're there. Okay. So just leave the recirculation. Come over here to electric panel. Yeah, put the rod lever at, always put the rod lever at neutral whenever you walk away. Don't ever walk away from the rod lever if it's at anything but neutral. All right. So do you see this little red circle at the bottom of the vertical gray sheet panel? That's our turbine. And to the right of it, if you follow the flow up and to the right, you can see the bus A transformer and the bus B transformer. We're going to want to flip both of those breakers. There you go. And now we are using power not from the grid, but we're using it from our own turbine. We're kind of dependent on ourselves, basically. And we're safe. That's it. Now we can use however much power we want, and we'll be fine. At this point, you're going to want to start figuring out what your demand is. So you find it on this computer up here. The demand currently is 350 megawatts, which is pretty low, if you ask me. Usually it's around 800, but 350 is fine. It's not that much. And I'm going to want you to meet that, not with the rods, but with the recirculation pumps. So increase both recirculation pumps until your reactor power is enough to reach the demand. Recirc is right here, by the way. It's those valves. Yeah, and be careful because these have a very quick effect on the power level. They're much faster than using the rods. Okay, we are going a bit slow, so you can go quite a bunch. We're probably going to need to go to about 20%, honestly. Just watch the period, because as your power changes in your reactor, the period is going to go down. So thus, if your power changes too quickly, it'll scram. A quick tip for determining what power level you need, or what APRM you need in order to meet demand, is to take demand, which is 350, divide it by 10, aka chop off a 0. So what is 350 divided by 10? So just take a 0 off of 350.
$35.
Yep, 35. So 35 is what we're going to want to put our APRM at. Ideally, like you're going to want to put it a little bit higher than 35, so maybe about 36 or 37, because we need to adjust for the power that we consume. So do that until APRM is at about 35%. So just recirc to that point. Well, I don't mean adjust recirc to 35%. I mean adjust recirc until APRM is at 35%. We're at about 28 right now. So we're almost there. And you can also see the auto balancer did a pretty good job. All the rods are white now. They're all balanced. They're pretty much the same power. So it did good. And you can also see all the rods right here. You can see the percent listed on them. You see how the ones in the middle, like 14%, 13%, those mean the rods are barely withdrawn, whereas the ones toward the sides are withdrawn pretty far, like 70, 60, 50%. That's because of what I told you earlier. The rods on the outside, they're cold because they're on the outside. They're exposed to coolant a lot more than the ones in the middle. So you raise power on those specific rods. Here, I'll highlight them for you on the little grid pattern down here. Those rods, you end up withdrawing them a lot more than the ones in the middle, because the ones in the middle are surrounded by more uranium and they generate more heat. Anyways, you're at 38% right now, and we're meeting demand, so you did a pretty good job. Yeah, So network demand is 350. We are sending 335, 336. As long as you are plus or minus 50 megawatts off of demand, then you're meeting demand. So come over here. Let's see how many points we're making. Look at that. Because we're using a lot of automatic systems, of course, we're not going to be making very many points, but we're making 0.167 points per second. Pretty good. Or, well, not good, but decent enough for a training, So how do you feel? That was a startup. You're done now.
I feel mind
How do you feel?
blowing.
Mind blowing. It's cool, isn't it? Yeah, I love this stuff. This is not even a complicated game. If you want a complicated game, you should play Ellsworth Generating Station. That thing is like 300 different buttons. It's a nightmare. Yeah, that's it. So I guess we could do a couple different things now. Let's see. We're gonna do some emergency.
Can you teach me how to do these manually?
Yeah. Yeah, sure. So don't come over to this panel, by the way. I set up some things. You're gonna deal with a off-site event in a little while. So, aka a loss of off-site power. But in the meantime, we're gonna talk about the manual panels. So, condenser, this is probably pretty simple. The SJs eject air. They're steam jet air ejectors. Let's turn off the auto and kind of show you how they work. So I want you to decrease the valve on just one of them by about 5 or 10%, and then watch the pressure in the condenser. See it going up? Yep, see that? It's going up pretty quick, isn't it? So they're pretty sensitive. This is not my preferred method to change pressure, even though it is the correct method. So, yep, put it at 100%, good job. My preferred method is to use the circulation, or the condenser, I don't know why they call it this. It's just the cooling water circuit, the circulating water. I like to use this valve right here, this pump's inlet valve, because the more circulating water you have going through your condenser, the more steam will be condensed because more cold water is flowing through. Thus, the greater the vacuum is going to be. So if you increase this valve right here, the pressure should go down because you're condensing more steam faster. So you want to try it? Look at that. Boom, it's going down. Make sense? Yep. All right. Go ahead and put it back at neutral, or sorry, yeah. Just try to stabilize it again, or you can turn on auto while we talk about the other stuff. All right, let's do deaerator. So turn off that auto on the deaerator. This thing, super duper simple. You just adjust the steam inlet and the gas outlet valve so that, oh, hang on a second. I am a little sick. Anyway, you see these red graphs up at the top of here? The deaerator temperature one is probably the most important. You're going to want to balance your temperature right at about 110 Celsius because it's like just barely boiling the water. Basically, it's just broiling it, kind of. And the steam in is what you use to adjust that. So if you lower the steam inflow valve, you should see the temperature go down because less hot steam is being admitted to the deaerator to heat it up. Make sense? You saw that, right? It's going down, now it's going back up. All right, cool. And then, careful. this is not a system you have to worry about. This is not a mission critical system. Like if you need to focus your efforts on something else, you can do anything else but the deaerator. If the deaerator has problems or if it's complaining and beeping, none of the other systems will care. This is just a keep the water clean kind of system. It's not that important. Anyway, yeah, it looks like you did it. You see the steam inflow. It says 7 kilograms per second right now. You just match the gas outlet to that, and that's all. AKA, pressure in equals pressure out, and then everything is balanced. As long as the temperature is good, which you balance with the steam inlet, and then the pressure is good, which you balance with the steam outlet, the gas outlet, then it's all okay. As long as, these red graphs and stuff are within the arrows, it's fine. All right, go ahead and put it back on auto, as long as you understand it, and then let's go to inert panel. We're gonna skip over MCC. That's a little mess. Let's do turbine. So turn off the auto for the turbine. It's pretty darn simple. The inlet right here is all the valve is all you really got to control. You lower the valve, less steam is admitted, which means pressure builds up. You increase the inlet, more steam gets admitted, pressure goes down, although you do make more power. So go ahead and play with that a little bit. See, you do make less power temporarily though. Like this is an interesting phenomenon. As you decrease the valve, your pressure will go up. But that also allows your water to get to a higher temperature before it boils, which means it'll be more effective and it'll make more power. So it's really weird, and there's a lot of like weird physics things that goes into it. But for now, all you really gotta remember is that this valve kind of dictates your reactor pressure. And it also dictates how much power you make. Right now we are way off demand because we let power level go really high. We're at 46% right now, so we're not meeting demand. But it's okay, we're doing training, so. All right. All right, you can put it back on auto. We don't need to worry about it, as long as you understand. All right, we never turned on this auto, but I'm gonna explain what it does. It's not terribly important. Like you can do it all yourself like we just did. This just controls reactor power through one of two methods, and that's used through these buttons right here, rod mode or recirc mode. See that? Rod mode allows the automatic control to reach your set point, which is adjusted with these buttons right here. Allows you to reach your set point using the rods. AKA it'll withdraw or insert rods to keep your power level at your set point. The recirc mode will increase or decrease the recirc flow in order to reach your power level as well. We don't really need to worry about that because we're doing okay on our own. Actually, that's pretty much all the automatic systems. Like this is an automatic system too, the auto balancer. Once it's balanced, you can turn it off. It's kind of like a ratio. Where like, right now, like it's 15-ish to 70-ish or 80-ish. And that ratio will always stay the same as long as you aren't fiddling around with a specific rod or anything like that. As long as you're just generally doing, entire core rod movements with the lever, the ratio will stay the same. The temperature will stay balanced, and all will be happy. So, that was it. Ooh, look at that. Prepare for disconnection from the grid. That sounds fun, right? Now, in an actual event, you're not given any warning. Same as real life, it just happens. Boom. Like some tornado or a storm or a tree will take down a power line outside and you will lose power to your plant. And although immediately you will still have power because you are running off the turbine, The turbine can't put its power anywhere. It can't offload the power it's generating to the grid because the line got severed, which means the turbine will trip. When the turbine trips, you are no longer able to feed your own power grid, which means your core will trip too. Your plant will have trouble. So when this happens, you're going to have to mitigate it and determine a solution to keep the reactor cold and filled with water without using any power. Unfortunately, in Unit 1, they don't really have very many creative solutions besides just the RCIC turbine. So what should happen is automatically the entire grid should scram, like your reactor will scram from a loss of offsite power, your turbine will trip, all these pumps will lose power. You'll lose power over here. Your lights will go off. I'll make sure they go off. There you go. Now your lights will go off when it happens. And then the RCIC turbine should automatically come on once the water level drops low enough, which it will. It'll start plummeting pretty quickly. So you just open the inlet a little bit, or not a little bit, you just put the inlet on max. You need to leave it like this. So you just leave it on positive, and it'll just adjust itself when the time comes. So there's not much you really have to worry about it. This is your safety backup. Like just put this on positive, and then you're good. That's pretty much it, honestly. So we'll let that happen. And in the meantime, while you are cooling the core, if you don't have the diesel generators already running, which we do, so we're fine. If you don't have them already running, you would want to start them up at that point when you lose power, because then you can power the green line and all your safety systems, like the Lipsy pump in particular and the shutdown cooling. Because, if you can't cool the core below 100 degrees Celsius, it'll start boiling and you'll lose water again, because you can't put water back in the core if you don't have power, unless you're using the emergency stuff. Yeah, honestly, you may just have to learn from experience, so we're going to do that. Yeah, 80 seconds. Yeah. You're fine, right? After this, I think we're going to go on a tour of the plant, and I'm going to show you the different systems, just so you can kind of get a sense of context and scale. That is, unless you have to go somewhere or leave or something. Anyways, you know what we're going to do? We're going to turn off your diesel generator. We're going to pretend like you don't know about this. You do not see that message right there. It is just a normal demand message, and you are a reactor operator. So go ahead, start, looking around at your plant and your different things. You're a normal grid operator. So you're a normal power plant operator. You do not see that message. Got it? This is a drill. So, do your normal stuff. Try to meet demand. Pretend for a little while. Yeah. Ooh, bang. Alright, you've lost offsite power. There goes all your lights. Look at that. Bang. Alright, what are you gonna do? What's the first thing you gotta do? Yep, get lights back on. That's okay. Alright, now you gotta start your diesel generator. So you gotta start up the blue line to diesel. There you go. And it should start running up. Yep, you just automatically put that on. See, now it's running up. But Unit 1, it takes forever to let it go. Next thing you gotta worry about is reactor level. Look at that. Boom, it's dropping. Negative 2.8, negative 2.9, negative 3. Ooh, that's scary. You don't have power for the pumps. What are you gonna do? 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 You haven't even scrammed yet. What are you doing? Scram the core. You're gonna start boiling too much. Scram. There you go. Alright, should stop. RCRC is forward. As long as reactor level doesn't go below -5, then you're safe. You're not going to melt out. Looks like it's paused right around -3.5. Check on your EEG. It's getting up to speed. It's almost there. Reactor's scrammed. Most systems look good. Your steam pressure is really high, but it's going down, so it's okay. Reactor level is going back up, so you are safe. You have averted the meltdown. So at this point, you should probably start slowing down your turbine so that you don't overfill the core. So decrease the valve so that it slows down a little bit. You don't want the reactor level to be super high, because then it'll trip the RCIC turbine, and then it might boil back down again. Yeah, so just decrease yeah, you did already. Never mind, you're good. All right, check on your EEG. It's almost there. So once that happens, you're going to want to enable the shutdown cooling, because that will bring your temperature down. So we will stop boiling water, and we will be able to, stay cold. All right, boom, it's cold. All right, sorry, it's run up. So come over here, enable shutdown cooling. These two right here, and you should watch the temperature drop pretty quick, because they are very effective. Look at that, doing their job pretty well. Steam pressure is still super high, and that is a good thing in our case, because like I told you, as pressure goes up, the boiling point goes up, which means if our pressure is high, less water should boil, because it takes a higher temperature to get there. If your pressure was low, below 3 MPa, for example, then you would have to use your Lipsy pump. But like you see over here, it requires power. It's on the green line, the Lipsy pump. But you're good. You are perfectly good. We are at 0.3 meters, 0.4 meters positive, so you're doing just fine. At this point, it's above 0 meters. You can go ahead and shut down the turbine. So go ahead and close the valve off, and then once it winds down enough, yeah, you can also just turn it off directly. That's fine too. Yep. All right, we're at plus 1.2 meters. We're fine. Once it goes below 100 C, we should stop boiling water, and then we'll be all good. Yeah, we're good. There you go, man. All right, that was a loss of offsite power. That's probably the most concerned, or the biggest thing you could be concerned about. So I qualify you as a good worker. Yippee! All right, what do you want to do now? You want to do that tour, or do you want to learn more about systems? Yeah, now we're at a high level, so. It's fine. We're all good.
HMM Lemma try to solo start up with your supervision.
Oh, you want to try to like full manual solo startup, or do you want to do like a full auto solo startup? What did you want to do? Full manual or like full auto solo?
Full auto first, cousin, still scared lol.
That's okay. First, we are going to have to wait though for the power to come back, because you can't start the reactor without offsite power. Unfortunately, I can't really cancel it because it's already started, so we just got to wait. It'll probably be like 10 minutes. Honestly, we might want to do that tour because it's just going to take a little while. We'll do it quickly. So, you ready? Wait a second. I think I just heard it. Did it come back on? Nope. Yep, you're good now. Okay, let's do it. No,
I'm going
it's
to
not.
get used to U1 first before moving to U2.
Yeah, U2 is a whole different beast, I'm gonna be honest. It is basically the same exact system, it's just made more complicated for the nerd. So, alright. You are below 50 degrees Celsius, so you are safe now. So, it recognized that as a successful shutdown, and the system is now connecting you back to the grid. It says 75 seconds now. So, just give us some time. And another thing you should remember is that offsite power disconnects always happen at the demand change time. So you know the timer that counts down for the demand and stuff. When that reaches 0 is when the game rolls a dice and decides whether it's going to do an offsite power loss event. So those are the times you want to be cautious, is when the demand change happens. All right, we're at 40 seconds now. So just give us some time. Once we get offsite power back, you can shut down your diesel or leave it on if you feel, like you want to. And then you can do your solo start. I think I'll just sit right here maybe. All right, 20 seconds. Any questions?
So far, so good.
All right, and you're reconnected. So you can see up here, line B is green. You have power through your startup transformer. All your stuff is good. You can probably, you could leave the green line on the diesel generator. There's no problem with that at all. But if you want to be realistic, you power the green line from the orange line, which is from offsite. So, all right, all up to you now. I don't know if you're able to type quick enough, but I would love to hear your thought process as you go through your startup.
Okay, first let me see what should I do. I think everything is okay. Should I turn off cool pump?
Only if you feel completely ready to go. Did you check your CST level, by the way? Yes, you gotta make sure that's in your checklist because, okay, so I don't think I told you this, but emergency systems like RCIC and LIPSI, they draw from the CSTs or the condensate storage tank.
CST level is at 6.9.
Yeah, 6.9. That's perfectly fine. I just wanted to make sure you checked it. because if there's no water in there, then the emergency systems can't put water back in the core or function at all, basically. And then you'll have a lot bigger of a problem during an emergency. All right, we'll leave it up to you now.
All right.
And in case you didn't know, there is a little checklist right here. So if you're ever by yourself and you forgot what to do, that thing will help you pretty well. It's not the greatest. There are a lot of things that I do differently from it, but just as a reminder, it is there.
I think I'm missing something with the reactor water level. Let us see what could go wrong.
Bro, I was just speaking the whole time without a mic. So the level that is expected, that's fine. It's due to a couple of reasons. Number one is swell. So as something gets hotter, its density goes down, particularly water. So as the water in your core gets hotter, it's going to take up more volume. And because the pressure vessel is a set volume, the level has to go up. So it's the same amount of water in the core. It's just, more volume is being taken out. That's why the level went up. Second reason, primarily, it's because we ran the RCIC turbine a little long. So you did start out at like plus 3 meters anyway, which is still pretty high. It should go back down once you start boiling steam out of the core. So give it a minute or two and you should get above 100 C and you'll be fine. Yep. And it is going to be harder to start up when your water level is high because it's a lot more water that you have to heat up to bring to boiling. Like if you ever boil tea or something like that, it takes a long time to boil a big pot versus just a small teacup for amount of tea or coffee or anything like that matter, anything similar. It was a risky move there, buddy. I saw you walk away from the panel while the lever was still in action. I know you got it. It's fine. It's just, there have been times when I was learning how to do this where I would just leave it on and then walk away and I'd come back and the reactor was at like 110% power and it would like instant scram. And then everybody in the server would get mad at me. So I'm just trying to save you from stuff like that. You don't seem like you'd forget though, so you're fine. That alarm is expected, so you're fine. I think it clicks on at 20% power. Forgot. Alrighty, good work. You can sink at 30% power. It is okay. The limit is 35. So anywhere between 10 and 35% APRM, you are able to sink the turbine. Okay, here's something I should probably point out. So for MCC right here, all of the loops, like all the levels, like hot well, deaerator, and reactor, they're all positive and they're nowhere near zero. That means you got a lot of extra water in the loop, and pretty much the only really big way to get rid of it is to use the hot well drain. Now you are using automatic control, so it's not really going to make sense to do it manually. So just turn on the auto hot well control right there. Nope, not turning off auto. I just want you to turn on auto hot well control, both of them. Yeah, there you go. All right. And then now it should automatically, see it's draining the hot well. It should balance out the loops so that your water level goes towards zero in all of the different levels. The other issue is it's taking that water and it's putting it somewhere. So it is putting it right in the CSTs. The CSTs cap out at 10 meters, which means they can no longer be drained into. So if you wait a little while, or not if you don't want to, you'll see it will stop draining because it's unable to because the CST is full. So the only way to mitigate this is to drain the CST. This is an issue. Well, you got to be careful though, because both of these things take a lot of power. So the hot well drain and the makeup, and the drain at the same time will take a lot of power. So we're at 23 megawatts right now is how much we're using. If we turned on the drain, we would break the startup transformer. Right now we're at 15, so we're fine. But now is the point you should probably see, look, it capped out. See, you're at CST of 10 meters. It can no longer drain even though there is water in the hot well. So turn off the auto hot well control. Turn off the auto hot well control, which you turned on earlier, this thing. There you go. And then now, that guarantees that it's not going to flip on and off. Like, cause for even a second, like this, it will just turn on for a second and then it'll break your transformer. So you're going to want to use the drain pump of the CST to bring it back down to about 6 meters. This pretty much just dumps the water back in the ocean. So the drain pump right here for the CST, click that on. There you go. There, yep. Now it's going back. Oop, my bad. Now it's going back down. Once it gets back down to about 6, you can turn it off and then turn the auto hot well control back on. This is just to prevent the startup transformer from, tripping or breaking. Because then if that happens, your feed water breaks and then your reactor scrams and then you'd have to do the whole process all over again. Yeah, it's a big deal. Perfect.
Did I miss something, or I cannot turn on turbine auto RPM?
You haven't set a set point for it yet. None of the buttons are clicked. You're going to want to click 3600. There you go. All right, now try to turn on. Oh, wait. Yep, I found the problem. So the valves have to be at neutral in order to use the auto RPM. Your bypass is at positive. There you go. All right, now try it. Try the auto RPM. Unless you want to keep waiting. That's okay. If you got something to do.
Reactor period is lowering.
Now, as long as it doesn't go below 20 or 30 seconds, it's fine. If it says 1 NF or infinite, that means it's perfectly stable. Well, almost perfectly stable. Basically, it just means it's too stable for the game to register. Does it work? Does it like turn on? Yeah, okay, good. I thought it was broken or something. Hey, be careful. You forgot something. You gotta put the turbine on auto pressure too. And you didn't close the bypass. So your pressure is super high. There you go. Yeah. That's okay for now, but you still have to close the bypass. The auto won't do it for you. And then you're going to want to switch grids. Oh, you had a startup transformer problem. So you use too much power, so it keeps tripping. Sorry, I got it for you. That was close. You lost power to all your equipment. See, your reactor level dropped a little while because the feed water pumps had an issue. Basically, you were cranking up the recircs, or I guess not, because they're 0 now, but I think I saw you did. You were cranking up the recircs, and I was using more power, and then eventually it used so much power that the startup transformer couldn't handle it, so it tripped. And you didn't see that because the lights were connected to battery, so you didn't have any visual indicator. So that's just, just warning you about connecting the lights to the DC grid. But it's all good now, because you're synced, and you're making power. Alright, good work, dude. You are meeting demand, and it looks pretty stable. So, we're going to do a little bit of a test. I am the grid operator, and we are demanding an extreme amount of power because it is, I don't know, the weekend or something. We're using a bunch of power. And we need 1.3 gigawatts from you. It's a lot of power. AKA 1,300 megawatts. So, go ahead and do that. Essentially, you're going to need to double how much power you're producing right now. Watch your power. It's increasing pretty quick. Alright, you're doing pretty good. Don't worry, you're good. You're good. Yeah, sorry. I jumped a little bit because I thought it was like at 100. Last time I saw it was at like 60, so. But it's stable enough. You can probably keep the recircs on max. It's fine. Yeah, you can max out the recircs. It's okay, dude. Yeah, recirculation pumps. There you go. You can max them out. Perfect. Ooh. Oh, we forgot about something. I'm so sorry. Yikes. That was on me. We forgot to enable the second feed water pump, so it was having some issues. Yeah, it's okay now though. Alright, how do you feel? Now, you're not making enough power, buddy. How are you gonna get to 1.3 gigawatts? You're not quite there yet. I know it's possible, but you're
I
not
feel
there.
mind blowing.
Yeah. You're gonna have to go manual. You have to pull the rods manually beyond 100% power. So be cautious and bring it to 1.3 gigawatts. The limit is 1.6. Your turbine will trip at 1.6. So we're not going to go that high. We're just going to go to 1.3.
Are we at 1.3?
You can check right here. You see the sent to grid thing right here. Do you see it?
Oh,
It says 12.5. So you need to put that at 1.3. You're almost there. It is going to be hard, but you can do it. It is possible. Alright, careful. There you go. You did it. 1.3. Alright, I want you to hold right here for a couple minutes. Don't let the power get too high. You know, don't let it go above 120, I'd say. Just hold it right here. Alright, first of all, before I go somewhere, any questions?
no, sir.
Alright. Yep, just be prepared for anything. Alright, back. Any requests?
No, sir.
Alright. As much as I want to make you do another offsite event, I feel like you've got it down pretty well because you handled the last one pretty nicely. So we're going to do something different. I'm going to have you shut down the reactor. Unless you want to do an offsite event at, 120% reactor power. That would be fun. But my vote anyway is to have you do a shutdown, because that is something that you might want to learn for something like a refuel or maintenance or something like that. So what you want to do, basically just do the reverse. Just bring power down low, desync the turbine after you've made sure you've moved back to the startup transformer, and then basically just shut down the core by inserting the rods, and then, turn on shutdown cooling and stuff like that. So just go in reverse of what you did to get here. Careful. Now, if you are feeling risky, a really good way to immediately drop power is to trip your recirculation pumps. Like right now, if you trip them, because they're running at 100%, they are a very big contributor to your reactor power. So if you trip them right now, you would probably go to about 50% power in an instant or two. But we're not going to do that. We're just going to have you get gentle all the way down to...
Okay, first to sync the turbine,
power
right?
levels. No, not right now, bro. Not right now, bro. Look, let me explain why. So, bus 2 primarily is why. Bus 2 or bus B is powered only by the turbine, and it has 3 things on it: condensate circulation pump 2, condensate pump 2, and feed water pump 2. Those 3 pumps are required to operate at high power levels. Your power level is still increasing, so just slam the rods in. Just insert them. Just insert. There you go. All right, just leave it. We can just let it go down. What was I saying? Yeah. So basically, you have to have those pumps running. Like right now, look, feed water pump 2 is running at 75%. If you drop that grid and this pump tripped because it wouldn't have any power, then your reactor level would plummet, and then you'd have problems. So you need to be at a safe power level where your facility doesn't use much power, so that you're able to switch back onto the startup transformer. AKA, you would do the opposite of what you did, which is turn on breaker 52BA2 instead of turning on the bus A transformer and bus B transformer. Not right now. Don't do it right now. You are at a really high power level. So, what power level were we at to sync at? We were at about 20-30%, right? For desync, you're going to want to go a little bit lower at about 10 to 15%. So basically just bring reactor power down to about 10 or 15%. Got it? And you're going to want to lower recirc at the same time. You're going to want those to be pretty low once you get down, because they do consume a lot of power. And it just lets you switch over to the startup transformer faster, so you can desync the turbine earlier. So, yeah, just slow down the pumps gradually. Yeah, honestly, slam them down. Just negative. Yeah, there you go. And then watch your power plummet. Look at that. Alright, now is the point you gotta be cautious. So, oh, what's that? It's fine. Generator always complains. You gotta be cautious, but power's dropping pretty quickly. Your rods might be too low, and it could just trip itself a little too early. Yeah, just be careful is all I'm saying. Anyway, so it looks like feed water pump 2 is no longer being used. It's at 0%, so you can turn off. So starter, pump starter, and then the outlet, and then the inlet. Pump 2, not pump 1. There you go, perfect. All right, condensate pump 2 is not being used either because the valve is below 50%, so you can turn off condensate pump 2. Cond pump 2, perfect. All right, and now circulation pump 2 can also be turned off, perfect. All right, ooh, look at that, we are 12% power, that's low. That is low. All right, research, don't need them anymore, turn them off, they're at 0%, that's fine. And then pull your rods out a little bit more, than your power level's pretty low. You don't want to desync your turbine early, that's bad. So pull them out more. Pull them out. You want more power. You don't want to desync early. All right, come back over here. Once that's stabilized, see, bus B is no longer being used. All the lights on it are red, so you can turn off the breaker 52 BB1. There you go. And look at our facility usage. Facility usage is 12 megawatts. That's way within the limits of the startup transformer. So we can switch over to startup transformer. So go ahead and do that. Perfect. All right, now the turbine can be safely desynced and run down. I would use the auto excel down, so go ahead and, well, there are a couple different methods for it. Ideally, you want to bring reactor load to 0 before you desync, otherwise it could cause damage because it'll slam it. But we're not going to do that. So just desync. So gen breaker. Yep. And then auto excel, but put the button on stop. Or auto RPM and then stop. Come on, you got it. The auto RPM thing right here. There you go, I put it on stop. Actually, wait, hang on. I forgot, there's a really cool thing I want to teach you. Yeah, okay. I'm going to teach you something called islanding. Islanding is a unique thing you do during losses of offsite power. It's only able to work when you're at a low power level where your turbine can exclusively and only power your facility. This is the procedure for it. You bring yourself to the correct power level. You use the auto run up, but you don't sync. You leave it so that it stays at 3600 RPM. Then, one second, you're able to come over here and you're able to go off of the startup transformer. So go ahead and only click the bus A transformer. See? All right, now we're islanded. We're island. I don't know where the thing is. Yeah, there it is. Okay, see the blue enunciator? It says islanding mode configuration. We are exclusively powered by our own turbine, and we are completely isolated from the grid. Yep. Anyway, that's islanding, so we can go back to the startup now. Startup transformer. Startup transformer. We can go back. Startup transformer. Free there. What are you doing, bro? That's fine. Come on, startup transformer. Switch it back. We don't need the island anymore. It's just teaching you that as a little fun fact. All right, now we can stop the turbine. So click stop. Click stop. So it's the left button. Right here. I'll click it for you. There we go. See? I click stop.
You see that? Where? Oh.
Look, here's 3600. Here's stop. Yeah. All right, I clicked it, and now we're going down. All right, cool. Now it will just take you back to the remote. Well, pressure is going up pretty high. That's fine. So we can lower power. You can bring it down quite a lot now, so you can just slam the rods in because we're pretty much in a shutdown configuration. So just put it on fast, throw them in. You can also scram if you want, but I don't like the alarms too much in this kind of shutdown situation. It's kind of out of place because it's not really an emergency. It's like, it's completely planned. Man, I am stuffy. I'm so sick. Oh. Okay.
Wish you health, man.
Thanks. Yep. Alrighty. So once those all go in, we can start, decreasing pressure a lot because that will help our temperature go down. And the way we would do that is by opening up that bypass valve once the turbine is stopped. So it's getting there. Just wait. Ugh. And you can also turn off the auto balancer. We're pretty cold right now, so we don't need it anymore. There you go. Otherwise, it will just fight you all the way down. It'll keep trying to balance the rods. What's that one? Low IPR. Yep, that's expected. All right, you can start downscaling your IPR M just like how you went up. So you click it down. IPRM down. There you go. All right, yeah. Might want to go again. Well, that's a bit much, but it's okay. We're fine. Turbine just does not want to slow down, does it? I mean, it's basically rolling on its own momentum right now. The bypass is pretty far open, and the valve is completely closed. So this stupid thing is just got a lot of momentum to it. Honestly, I'm impatient, so you want to slam the main valve. So close the main valve. Bang. All right, it's isolated. Now we can open the bypass fully so we can start decreasing pressure. And this will give our condenser a little bit of trouble because we're basically dumping a bunch of steam on it. But it can handle it. It's fine. Yeah, see? All right, and as pressure goes down, temperature should also go down too because, all the hot water will boil out as the boiling point goes down. And we are at 0% power. Rods are going in. If you want to put in rods faster, there's a method where you do this. You click all the rods. This kind of gives it like a little boost almost, and you have to put it on rod mode. So here's all, and then here's rod mode, like that. And then you click off the ones that are already like fully done. So the middle, that's all done. And now it'll kind of redivert the insertion power to the other ones. So it kind of helps insert them faster. Or we can scram. We'll just scram. This is a perfectly applicable application. So just scram it. This is what real life operators do. They just scram it when they want to shut down. It's a normal thing. It's not an emergency only. So here, click it. Scram the core. Scram the core. Scram the core. It's okay. There you go. All right, that's all good. And now we're shut down. Almost. Now you can use shutdown cooling and start getting us cold. Perfect. Both of them. So we get colder faster. Awesome. Okay. All right, now is the point where we start turning stuff off that's not being used. So the recircs, we only need them for power operations, so we don't need them anymore because we're shutting down. So go ahead and turn off all the recirc stuff. You can just click them all. The order does not matter. It's just a professional thing. Just click them all off. There you go. Perfect. All right. Bypass 100. Feed water. That one's good. That's good. We no longer need the preheaters, so you can turn off the preheaters. Yep, it's going to make a noise. So just acknowledge that. All right. We still are generating steam and we still have pressure, so we can't quite shut down the condenser yet because we still have to condense that all. It's honestly just a waiting game at this point. So, but yeah, in my opinion, we're done. That's a shutdown. Guys, shutdown cooling is on. You're on the startup transformer. Everything is safe. Like, only other consideration I would have is that we want to be at the correct temperature because we are still at boiling temperature right now. So if we wait a little bit longer, then it will be truly safe. Shutdown cooling is taking a long time. We could also shut down one of the SJs. So condenser pressure is still going down, even though the auto control is trying to handle it, which means there is very little steam. So we're ejecting too much. So we can just turn off one of these ejectors. So just turn it off. Turn off one SJ. There you go. All right, pressure should go back up, and then the auto control can handle it using this valve right here. See, you always want to have the autos have some wiggle room, otherwise they go out of range and they can't do any work for you. Man, this is taking a while. I never remember taking this long before. Shutdown cooling is usually pretty fast. All right, we're below 100. Should start going faster. And we should have less steam. Yeah, look at that. Pressure's dropping. We're no longer boiling. And then all of these should start going to 0. And then we can start turning pumps off and stuff, and then we can go do a tour. What's that? Oh, yeah, there's no vacuum because, well, yeah, there's no steam to make a vacuum with. So, turn off our SJ, turn off the circ valve, turn off auto. It doesn't matter anymore. There's no more steam to condense, so we don't care. All right, that can do its own thing. Reactor is cold. We can turn off feed water. Yeah, pretty much just turn everything off. It's all good now. All right, you ready? We're gonna go. We're gonna look around. It's all safe. You don't have to worry about it. It's cold. There's water. There's power. It's fine. So let's go. Let's go show you around the plant. So here's Unit 2. Have you been in there? It doesn't really matter. We'll go look for a second. It's basically the same thing, just different. So we don't gotta worry about it too much. Let's go. All right, grab a dosimeter. This will track how much radiation you've accumulated over your journey. Always close those red doors behind you, because otherwise people will get locked on their side. Let's go to the reactor hall first. This is for Unit 2, by the way. All the equipment in the facility is for Unit 2, because Unit 1 is it's a little bit of a trainer. It's not really a trainer, but it kind of is. So here's the reactor hall. Here is like the bottom of like that light bulb shape is the concrete barrier to the dry well. Here's a stairwell over here. We're gonna go all the way up to the top. All right, here's the reactor hall. Here's your lid. Have you ever done a refueling before?
Nope.
Have you ever done a No? Okay. So beneath this is the drywall head, and then beneath that is the pressure vessel head, and then inside there is all the fuel rods and core and everything. It's really fun. I just did one earlier today. They take about an hour and a half to 2 hours to do, so it's a pretty lengthy adventure. Anyway, below this, I'd say about probably about 50 meters, or like 180 feet, is ground level. So we are really high in the sky right now. The reactor is pretty tall. Inside the drywall, so the drywall is like a second skin almost. So you have the pressure vessel. Inside the pressure vessel is all the water and the core and the fuel and the control rods and stuff. But surrounding it is the drywall. It's a containment structure And the recirculation pumps are inside there as well. We're going to go all the way down to the bottom. I'm going to show you around a little bit. These are the accumulators. These are like the control rod drivers. They have a bunch of pressurized water and nitrogen, and they move our control rods and our core because, you have to move them somehow. Let's see if we can go to the reactor hall from here. So we just climbed a pretty big stairwell, if you ask me. So we're pretty far down below. Here is the core, or the reactor vessel. Here is a drywall entrance. We can't actually go there because the devs haven't modeled it yet. This is like an equipment hatch. It's what they would use to put the recirculation pumps through when they were first constructing it. There we go. All right, over here. Now we're kind of in the loading bay area. Oh, hold on, I forgot something. Let me show you. We're back here. Yeah, my nose, man. This is so bad. Over here. These are your kind of like isolation valves almost. This is where steam comes from the drywall and the pressure vessel, and feed water goes back in. This is like the big transfer room. These red things, those are valves. Let me show you back out here. Where'd you go? There you are. These are the main steam lines from Unit 2. Pretty sure Unit 1 is over here. Yeah, here's Unit 1. Unit 1 is not modeled. Like I say, it's kind of a practice. So here's the steam lines. They take steam and it goes to the turbines. Turbines are over here. Let's go this way. So here's the generator. Here's the exciter. It's like a voltage source. There's 3 low pressure turbines. Here's turbine 3, turbine 2, and turbine 1. Here's the high pressure turbine. Here's the stop valve. Remember that main valve thing that you would click so that you could open the thing? That is these. These guys are here. They make a really big noise when you open them in Unit 2. It goes clunk, and then the whole hall echoes. It's really cool. Anyway, the main steam lines are these things right here. That comes from over there where we were earlier. It goes in to the high pressure turbine. It goes back out to these moisture like reheaters, which kind of dry the steam so it can be sent into these. These extract a lot of the energy. The generator right here generates your power. Down here is your condenser. I kind of went really far, didn't I? It's pretty big. So this whole area, here's one section. These are the cars, by the way. These are the car pumps. The things you use to initially get rid of the air of the condenser, the car pumps. Here's car 2, I think. Yeah, and you see, look how big these water lines are. These are your circulation water pumps. They're used to cool the steam down enough so that it turns into condensate. Pretty big. It's a lot of water. It's like tens of tons per second. Like it's a lot. Here are pretty sure these are the condensate pumps. Forgot exactly. Here are the polishers. We didn't really talk about these, but they're similar to the deaerator. They just kind of clean up the water a little bit. Here are your SJs. You can kind of hear them hissing a little bit. They have a nozzle inside of them, like a rocket nozzle, and steam blows through. It sucks air with it, thus lowering the pressure in the condenser. All right, yeah. All of that was Unit 2, but Unit 1 is just mirrored over here. So that's Unit 1. Don't really got to worry about it because there's nothing too interesting. Let's go back up. Actually, let's go this way. Forgot to show you something. These are... Oh, where'd you go? Over here. Yeah, come down. These are fire extinguishers because Unit 2 can catch on fire. Those are used to put it out. Here's the basement. I love this place. This is like my favorite place ever. Let me find the room. Yeah, cool flashlight. Here is feed water. So over here, where'd you go? Here, there you are. Hi. So feed water pumps right here. They're big. They're really big, aren't they? That's why they take so much power. They take like 10 megawatts each. Here are your preheaters. It's just a shell and tube type preheater. The steam comes in. Oh, I'm so sorry. The steam comes in, the water comes in, it gets hot, so it's more efficient, and it goes to the core. Alright, one more thing, and it's outside. So I'm gonna go ahead and reset. So come this way, I think. Let me see where I am. Yeah, come this way. We're gonna have to walk quite a bit, so. So here is the switch yard, by the way, as we pass through here. This is where power gets kind of connected to and from the grid. You can see all the transformers in there and the lines. These guys right here, these big gray like poles with the the big things on them. Those are like the breakers. If you have a loss of offsite power, these things will flip up. It'll cause a big purple arc to go in the sky. It's really cool. I actually have not been able to see it before because they're kind of rare. Anyway, that's the turbine hall back there, the black, like blue building, and all the power comes out here through the switchyard, and it goes on electric poles. There's big transmission towers, and it goes to the city or the grid. Here are the cooling towers. These take the water from the condenser that was used to cool the steam, and then it cools that steam, or it cools that water with the surrounding air. So I don't think they modeled it, but we can take a peek inside. Nope, looks like they blocked it off. Anyway, inside of a cooling tower, there's a big pool, and in that pool is like hot water, and the hot water evaporates through the air. That's why you see a lot of like steam. Some people call it smoke. It's not smoke, it's steam. Steam comes out the top of these. They look this way. They look in this curved shape because they're called hyperbolic natural draft cooling towers. What that means is that it uses like natural air circulation to move the air around to cool the water off with. Because as air gets warmer, it gets hotter and it becomes less dense, so it wants to float. And all that floaty air collects to the bottom, gets squished up through that funnel, and gets kind of ejected out. It's really cool. It's like an air engine or like a rocket nozzle almost. Kind of the same principle as those SJs. So you can kind of see the water, the big water lines. You see these guys, look at that. Huge amounts of water come through here. Anyway, let's keep going around. We're almost done. So this is the cask processing area. It doesn't actually do anything right now. But we can go inside, we can show you. So this is where spent fuel is stored in these large dry casks. They're huge amounts of concrete. They weigh probably like 200 tons. And they can take essentially a whole train. Like you can put these things on a truck, you can hit them with a train, and that train will blow up. These things will remain unscathed. They're kind of invincible. They're really good at holding waste. We're gonna keep going. So that's the high level waste, aka the really radioactive stuff. This is the low level waste storage, aka like filters and things and stuff that's not super radioactive, unlike the fuel rods are, the spent fuel rods. You won't actually ever do anything over there. It's just cosmetic. Over here is oil processing for like the turbine and stuff. You don't really got to worry about it. There's nothing in there to use. Over here, however, this is kind of important. This is the EDGs. Over here. Yo. These are the diesel generators. So here's unit 2, number 2. Here's unit 2, number 1. And then here is, you can hear them running right now because you left the switch on in unit 1. And these are your diesel generators that you use for your backup grid. Your green line. Alright, let's keep going. Let's look over here for a second. I don't know if you can zoom out and look, but over here, let's go this way. This is the service water cooling pods. So like water used to cool the oil systems or the different things that need to stay cold for operation, like pumps. This is where the water gets cooled. It's very, very similar to the cooling towers. Like inside a cooling tower, this is what it looks like. It's just a cooling tower has that shape on top of it that move the air around faster. These things are just kind of let it be. All right, let's go back over here. These are big diesel tanks. They need to be refueled sometimes, and you have to call the operator. We're going to go to one more place, or two more places. All right, over here is kind of like your water treatment. Remember that CST makeup pump? This is where it gets that water from. These big pumps right here, these are your makeup pumps. Over here is the kind of like pumping station, I think it's called. It takes in seawater from the river. You can see right here, see this intake. It goes through, yeah, you can go in there. Yeah. Over here it goes through marine, like sea life filters. You will fall through, so don't walk on those. Those kind of like take the fish out and stuff before it goes to pumps, because you'd be surprised how many times that's happened. Not in RBWR, in real life. In real life. I don't know what those are. All right. One more place, I think. Yeah. Here's your cafeteria. It does not have anything special. It's just very expensive donuts and some radioactive goo and maybe a coffee. All right, we are going to have to go through the systems again because I did forget about this place, but it's okay. It's not too far away. I always use the employee entrance. I don't really do the elevators because they're kind of slow. Here's a training room, by the way. If you ever find somebody or you want to practice, you can practice in here. You know, here's your rod control, here's your MCC, here's your turbine. Anyway, going back. We're going to go to level 3. Oh wait, let me show you this place. I think you've been here before. I think that we'll come back up. Come to level 4. Sorry. Or floor 4. Where'd you get here? This is the supervisor's office. I'll kind of open it up for you to show you. Where'd you go? Come back to the stairwell. Where'd you go? Oh, there you are. You just kind of glitched out for a second. So, okay. Alright, you see it? You can't go in there because you'll get kicked out, but it's just a fun room for like managing like demand and stuff like that. It is really cool. And it's got weather. Alright, back down to level 3. We're going to go to the CST hall. Level 3. There you are. Alright. Kind of a really backwards tour I'm giving you, huh? We have to grab an energy similar because we reset. One more place. Well, yeah, I keep remembering places to show you. 2 more places, I promise. Only 2 more. Come on, click it. There you go. Alright, come on. Alright, 2 more places, my bad. Here's the deaerator. It's basically just a really big, like, boiler steam drum kind of thing. So, like, water comes in through this pipe here from the polishers. And then it goes through the top, gets kind of mixed with steam and stuff. The gases get mixed out. And then down on the bottom, I don't think it's bottled, but on the bottom down here, the feed water goes to the pumps, which are below us. All right, one more place. All right, let's just jump. Whee! Where is it? It's over here. Here are your condensate storage tanks. Pretty big. It's a lot of water if you think about it. Anyways, yeah, here are these pumps. I think that's it. That is our tour. Alright, any thoughts or anything? Or is that it?
Wow.
Yeah, very cool.
I have no
Yeah.
questions.
Yeah, we'll let you be now. That's cool. Alright. Let's go back to the exit, I guess. Well, I could show you one place. Down here is the MCR, or 6. It's where you do polisher stuff, like polisher regeneration, because it's got chemicals and stuff. Yeah. You'll figure it out later. Down there is the basement. We're not going to go there. We're going to go back up. Here. Do you want to see TCR? Have you been in TCR before? TCR is up above us. It's just the turbine control area.
Number.
here is more polisher stuff. It's a chemical lab. You can do testing and stuff in there. Yeah, that's it. All right. Anything else you want to do?
All good.
All good? Okay. I guess I'll see you around. If you know anybody that wants another like tutorial or tour or anything like that, just let them know. I'm always looking for people to teach.
So yes, sir.
Hopefully I'll be less sick next time.
Thank you
Yeah, see
for
you
your
around.
time.
Yeah, you're welcome, man. Don't worry.
You
All right, have a
helped
good
me
day.
a
See ya.
lot.
Bye-bye.
Bye.